Welcome to Module 7 on black holes. Black holes are a very exotic entity in the universe. And one way to describe them, they are astronomical objects that don't release light. They're so dense. Now, it's interesting how this first came into the human imagination. Few people know that it was actually the 18th century. This mathematician, Peter Laplace, just asked a question. It's just occurred to him to think about escape velocity. He's not the first person to ask that question, but let me talk about escape velocity first. If you have an object, here like a planet, the gravitational attraction of the planet is going to determine how fast an object has to move away from the planet in order to escape altogether the gravitational effect. So that here on the planet Earth, for instance, if this were the Earth, then if we have an object that's moving 7 miles per second right here at the surface, it will move all the way to infinity if given enough time. It'll actually completely escape the effect of the Earth's pull. Now, if it's moving 8 miles per second or 100 miles per second, all of those velocities are going to enable it to entirely escape. Anything less than 7 miles a second, it'll go up for a while, it'll come back down. So Laplace asked a very simple question. He said, what if you made the planet more massive and larger, so much so that the escape velocity approaches the speed of light? And so he did the mathematics and found out that if you have a planet of the same density as the Earth, but 250 times as big as the Sun. So now I want you to imagine a large planet, 250 times the size of the Sun. The Sun is 1,000,000 times the size of the Earth. So now we're looking at something 250 million times the size of Earth, same density. Then the escape velocity is the speed of light. So if you add one more little pebble to this large planet, then nothing can leave because nothing can move faster than the speed of light. This is Einstein's special theory of relativity. Nothing can move faster than the speed of light. This large planet then would be a black hole because we would not be able to see it. Now, it's kind of typical of scientists to imagine things and just to see how it looks mathematically. I don't actually know this, but I didn't find anything where Laplace thought there would be an actual black hole. But in the 20th century, we've gathered data and we've begun to find actual black holes in the universe, where typically a star will have a partner. It'll be a binary system. And so we're able to see stars that are losing their material, and it's disappearing, and it's rapidly accelerating the material as it leaves the star. And so we're picking up X-rays from this acceleration, but there's no companion. So the hypothesis, the theory is that these are black holes out there. And our present understanding is that in the center of the Milky Way, there is a black hole, which it's a large one. It's 1.3 million times the mass of our sun. So that's the image we have right now of actually most galaxies. The center is so concentrated that it has reached a place where nothing can escape it, a density. And so what's happening right now then in the center of the Milky Way is that the black hole is gobbling up entire suns. And as it does so, it grows in size. So that is that's the amazing story of the black hole. But there's another part to it that is even more, I guess, exotic. And this is now just based on the mathematics. This is speculation. It's the same kind of speculation that Laplace entered into. if you look at the mathematics of a black hole, they are always associated with another mathematical object. But the difference here is that if a black hole is something that doesn't give off light, but will absorb, so for instance, the black hole of the Milky Way is absorbing entire stars, it sucks them into itself and releases nothing. The mathematical object that is attached to every black hole is a white hole. So it's a place that does nothing but give birth. So matter and light is exploding out of the white hole. There's no evidence that I know of, that I've read about, there's no evidence for any white hole in the universe. So we're in that interesting state of we have a mathematical idea without any empirical observational evidence. Is it real or not? Some scientists are already imagining it is real. This would be a standard way of moving in science, so that at the beginning of the 20th century, early part of the 20th century, Paul Dirac, English physicist, was looking at the mathematics of quantum mechanics. And he noticed that mathematically there was this object that he called antimatter. And so no one had an idea of antimatter, but it came out of the mathematics. Scientists began looking for antimatter and indeed found it. And now we know that every particle has an antiparticle. So it could be that there are white holes in the universe. And one of the physicists, Lee Smolin, who is reflecting on this, is using this idea in an interesting way that I thought I would just conclude with. In his view, what is happening is that the universe is being absorbed into a black hole, but then it travels through, and then it comes out of a white hole, so that the universe in a certain sense is being recycled. And he has the further theory that those universes that come forth with very particular characteristics, like long burning stars, and like an expansion rate that holds open for a long time, those universes are the ones that will be around longer, obviously, than the short-lived universes. So that, in Smolin's view, this white hole, black hole dynamic is the reason we find ourselves in a universe that seems to be so powerfully designed or shaped for the appearance of life and intelligence. Again, it's speculation, but it's connected to the mathematics of black holes, which we now know are real.